Okay, so here I want to talk about some of the limitations of regression. Um, one thing is that to sort of keep in mind is that even if the, the the data is close to a straight line, um, it might be a part of an overall pattern that's not linear if you continue in either direction. And so that's you have to be careful about making predictions outside of the x values for your original data. So in this example here, we had the birth weight of 10 babies, and that's the same data set we worked with before. If we just look at the weights of the babies between 32 and 42 weeks, they're reasonably close to a straight line, but the straight line here is in yellow. If we continue that straight line in the to the earlier weeks, we get into some negative weights, so that the fetus after 10 weeks would be, the predicted weight of the fetus would be negative 50 ounces. And that's clearly not realistic. So yeah, the issue is that growth with unlimited food supply follows an exponential pattern, and so it's not a straight line type pattern. And so with the exponential pattern, the slope gradually increases. So between 0 and 5 weeks, you have almost zero slope here, but now it starts to get the slope starts to get a little bit positive, and the slope increases as the number of weeks increases. So it's not with a straight line; you just have one slope. It's the so this is an exponential pattern. Now, if you have data from let's say the 10 to 20 week range on the weight of fetuses in the womb, you could fit a straight line there. But it would be a different straight line. Right? You could fit a straight line to that time period, but it would be a different straight line, different slope than the one that we had computed using the data. Yeah, growth with unlimited resources follows an exponential pattern, and that's not the only thing. There's also money. If you invest money at a certain percent interest rate, and for the first year, maybe you're earning money mainly on the your original investment, but after the second, third year, fourth year, fifth year, so forth, you start earning money on the interest in addition to earning money on the original principal. So the slope is not constant again. You have an exponential pattern there. And the same if you borrow money. If you borrow money, you're going to be paying interest on the interest, so to speak. So it's anyway, there's certain things that follow an exponential pattern. So you have to be a little bit careful about making predictions into the future or making predictions into the past. If you do, that's called extrapolation, and you just have to be cautious about extrapolating. Sometimes you can't avoid extrapolating. So some other terminology here. If a point has an outlying x value, that's called a high leverage point. So Sophia was born after 32 weeks. That was an outlying x value. That's called a high leverage point. And if it has a big effect on the slope, That's also called an influential point. If you compute the statistics without Sophia, we have a correlation coefficient of 0.7 instead of 0.9, so that's a pretty big difference. The slope and the intercept are not much affected. So Sophia would not be an influential point. It did have a big effect on the correlation coefficient, but it didn't have a big effect on the slope. Yolanda had above average gestation, below average birth weight. So Yolanda's, I think this might have been Yolanda right here. This is Yolanda. She's not the lowest birth weight. She's not the highest gestation, but she had an unusual combination of birth weight and gestation. So she's another one that is possibly an influential point there. Above average gestation, below average birth weight. Yolanda also had the highest squared residual. So that's an indication there that Yolanda is going to have an impact on the on our statistics. She had the here's Yolanda. Yolanda. It's 41 weeks gestation, 100 ounces, and she had the highest squared residual, 165. She was more than 1/3 of the total squared residual. The total squared residuals was 417, and of that, Yolanda's was 165. So she had a big effect on the total squared residuals. And if we compute the statistics without Yolanda, we have a correlation coefficient of 0.95 instead of 0.91, so there's a difference there. The y-intercept, -125 instead of -109.7. The slope, 5.86 instead of 5.42. So Yolanda had an influence on R and B and A, and because Yolanda had a big effect on the slope, we say that Yolanda's point was an influential point. Okay. Okay. So we talked about the dangers of extrapolation. Another sort of limitation of regression is that it doesn't say anything about cause, and it's easy to jump to conclusions about cause. Like we might think that the longer pregnancies cause the higher birth weight, but there could be other variables involved. So we have to be careful about jumping to conclusions about which causes which. But anyway, if you have two variables with a high correlation, variables A and B, it might be that A causes B, it might be that B causes A, it might be a third variable causes both, or it could be coincidence, especially if you have a small data set. So as an example, there's a study of public school students between the ages of 5 and 18 years. It showed a strong positive correlation between the number of cigarettes smoked per day and lung capacity. In other words, the students who smoked the most cigarettes tend to have the largest lung capacity. And which of the four following possibilities is most likely? So smoking increases one's lung capacity, larger lungs increases smoking, a third variable increases both, or coincidence. And this was a large study, so it's probably not coincidence. And we know that smoking does not increase lung capacity. If anything, it decreases lung capacity. Smoking damages your lungs. Anyway, if you think about the age range here, these were the age range went from 5 years to 18 years, and it's likely 5 years they're still children. 18-year-olds they're close to being adult. They have adult-sized bodies, and So the 5-year-olds are more likely to have smaller lungs, not because they don't smoke, but because they're not fully developed yet. And the 18-year-olds are likely to have larger lungs, not because they smoke, but because they're more fully developed. So the increased age, and also from what we know about who smokes, the teenagers tend to smoke more than the 5-year-olds. So we would say the increased age affects the amount of smoking they do, and also affects the lung capacity. So that would be, and that the mathematics really doesn't tell you which of these 4 possibilities is the correct one, but you have to just think about what makes sense in the situation. I also want to mention a little bit about experiments versus observational studies. The study of smoking and lung capacity was an observational study. Observational studies record but do not control the variables. And that makes it very hard to prove cause with an observational study because there's maybe additional variables. Experiments control the variables, and that makes it easier to prove cause. But for ethical reasons, experiments are not always possible. So, for example, an experiment to see if smoking causes lung cancer might require randomly deciding which people smoke and which people don't smoke, and then recording the cancer rates for each group. So you can't tell one group of people they have to smoke for 30 years, and then another group of people they can't smoke for 30 years, and that would not be ethical. So that was one of the reasons it's very hard to. It took so many years to before the Surgeon General was able to determine that smoking causes lung cancer. It was the observational studies suggested that was the case, but they didn't really prove the case because there are so many other variables that could have been affecting the cancer rates. But finally, the Surgeon General just decided he's seen enough evidence, and that's when they put the warning messages on cigarette packages. I think that was in the I think it was in the early 70s, if I remember right, 1970s. Okay, so that concludes this presentation.